Hello everyone. Today we will discuss Lecture 5, Chapter 4, Volcanism and Igneous Rocks. We're going to break this lecture into three parts, first discussing igneous rocks definition and formation, then discussing how to classify igneous rocks, and finally to discuss volcanic hazards and the plate tectonic context in which igneous rocks form. This picture on your title slide is of Volcán de Fuego erupting near Antigua, Guatemala. Guatemala is a country with a lot of volcanoes, and the reason why there are so many volcanoes there is discussed in part 3 of this lecture. Your lecture activity for today is to find a job posting on the internet where the individual studies igneous rocks. The key here is that they study igneous rocks, not other rock types. So I want you to use the information learned in the lectures to determine what igneous rocks are and if this individual studies them, works to study them. Some places to look for these jobs are usajobs.gov, a typical Google search, state geological agencies, and postdoctoral research positions. I'm going to ask you to follow the instructions below, writing down the link and the salary, the duties of the job, etc., and to turn it in for a lecture activity. So you may pause the video now and record this information. Part 1 of the lecture discusses how we define igneous rocks and how they form. So first let's talk about magma and lava. Volcanic eruptions are manifestations of igneous activity where rock melts deep underground to produce magmas, and when that magma reaches the surface at a volcano, it becomes a lava. So at the exact point it reaches the surface, when the magma either explodes or flows out gently of the volcano, it becomes a lava. So we see on the top two slides or top two images here that we have lava pouring out of volcanic vents and into ocean and on land in Hawaii. The three main ways in which rock melts are called decompression melting, flux melting, and heat transfer melting. These are a little bit complex, but we'll devote one slide to each method. So these photos, again in 2018, were from Kilauea eruption in Hawaii, and the bottom left photo is from Mount Vesuvius in Pompeii in Italy, which has very famous historic eruptions. Decompression melting occurs as hot material rises beneath Earth's surface, and as a result, its pressure decreases because there's less weight on top of it. So as the pressure decreases, the melting point of the rock also decreases. And this is a result of a thing that we have called the geotherm, where temperature increases with depth within Earth, and the solidus, which is a line, curved line on a graph of temperature and pressure, where a melt begins to form from a solid rock. Similarly, the liquidus line on this plot is when a rock is completely melted. So on the left-hand side of the plot, we've got totally solid rock at high pressures and most temperatures. But if we were to go from point A to point B, where we decrease the pressure, we may hit the solidus. We may hit the solidus and begin to melt the rock as we pass the solidus. Once we hit the liquidus, we are totally liquid. This type of melting occurs in mantle plume environments and can also lead to hotspot volcanoes like in Hawaii and Yellowstone. This also occurs at active rifts and mid-ocean ridges. So as the magmas, as the rocks are becoming decompressed, as they rise closer to the surface, they begin to melt in these types of tectonic environments. Flux melting occurs as a result of the addition of volatile material, also known as flux, to rocks in the asthenosphere, which reduces their melting point. So these volatiles are most commonly water, carbon dioxide, other fluids, and this type of melting occurs at subduction zones due to the presence of water that is a part of the subducted plate. So the rocks in the subducted plate are hydrated. They have some water in them, either as H2O or as hydroxide molecules, which are known as OH chemically. And this structural water in them eventually gets moved up and evaporated and goes through the crust above as the subducted plate goes down, and this causes melting above. Heat transfer melting is the transfer of heat from hot mantle rock to cooler continental crust, and that causes melting. So this is known as conduction. Think of an electric burner on your stove transferring heat to a pot of boiling water, for example. And this heat transfer melting is associated with hot spots and rising mantle plumes. So hot spots and mantle plumes have two types of melting associated with them, working together with each other. So now let's talk about the different types of magma. Magma varies in its elemental or chemical composition, and the key variation in composition is the proportion of silica atoms, Si, to iron and magnesium oxide molecules as they are measured from analytical equipment. So table 4.2 shows the four major types of magma: felsic, intermediate, mafic, and ultramafic. And you can see that silica content increases in percent as you go from ultramafic, which is very low, to felsic, which is very high. So felsic rocks in turn have low iron and magnesium oxides, whereas mafic and ultramafic rocks have high iron and magnesium oxides. An important piece of knowledge about the magma composition is that it forms in an orderly pattern all around the Earth. So ultramafic rocks crystallize at high temperatures, whereas felsic rocks crystallize at lowest temperatures. In addition to those criteria, felsic rocks are highly viscous, meaning they have high resistance to flow as a result of their high silica composition. Those silica tetrahedra do not flow very well if you're looking at the atomic scale. And then the ultramafic rocks have a very low viscosity, so they do flow well. Imagine Hawaii lava flows rolling across the landscape. This doesn't happen with felsic melts and felsic rocks. So another important way to think about these different types of magma in terms of their composition is their mineralogy. And Bowen's reaction series is the best way to illustrate this. So because not all rocks melt at the same temperature, Bowen's reaction series shows us the order in which minerals crystallize and form rocks at the different temperatures. And this process of crystallization or freezing of minerals in rocks at different temperature steps is called fractional crystallization. So using Bowen's reaction series to the left, what minerals do you think could be present in both mafic and felsic rocks? Do ultramafic rocks come from low or high temperature melts? And what do you think is meant by continuous series and discontinuous series? I encourage you to think about these questions as we move forward. A really great video on how igneous rocks are formed, starting with melting from the mantle, is provided by Dr. Stephen Marshak in a video, and I'll provide a link to that video. But let's talk about formation of igneous rocks. What causes magma to rise in the first place? Well, magma, as it melts, has a lower density than the solid rock around it, so it will rise through the existing rock. Pressure from overlying rock also squeezes the magma upward, Just imagine walking through bare feet in the mud. As you add more pressure to the mud will squeeze up through your toes. And also just remember that the mantle is solid, at least most of it is. And so as these rocks begin to melt, they're pushing themselves up through the cracks and pushing out the more denser rocks, which is sinking. The rate at which a melt cools, which is also known as freezes or solidifies, depends on a variety of factors, including the composition of melt, where the cooling occurs, for example, at the surface of Earth or at a depth below the surface, the shape and size of the magma body that is cooling, and the rate of heat transfer from that magma or lava body to the surrounding area. Importantly, melting of rocks to produce igneous rocks also produces gases, known as aerosols, which are tiny particles of solids or liquids that are suspended in air. And some of these, some volcanic gases like water vapor, carbon dioxide, and sulfur dioxide, which is toxic.